It's a beautiful day today, no?
Mhm.
All right. So we have that going for us at least.
Okay, after my midterms.
Yeah, people getting hammered by midterms, huh? All right. What else is going on? Any problems with assignments? Anything broken in Moodle you want to tell me about? No? All right. I think we are like exactly, this is the halfway point week of the semester for us. So, yeah, I think maybe today, I said this last time, but maybe we'll get through the sun today. We still need to talk about fusion. Didn't quite get there. It's okay. We will move on. We need to start talking about the other stars. And the next task on our list is figuring out how to classify stars. So that's going to be a little bit of a job because, yeah, they ostensibly look quite the same when you look up at the sky. And it's very difficult to tell when something is nearby or whether it's just really big. And so we're gonna figure out if we can get closer to that. Some unsolved mysteries there too, so it's not quite a simple story. But first, same as every class, what is the essential crux of the astronomical story that we're talking about in this course? Back row, I'm looking at you guys.
Expecting that all of you wrote it down.
Yeah, did anybody write it down last time? I literally gave you the answer to this question. Come on. Yeah? Royce, you got this?
Well, I don't know like the whole like answer, but like is the sun gas or liquid?
There you go. That's a good place to start. Is the sun a gas or a liquid? Why does it matter? Who cares? Yeah. Issy.
We can like to figure out if we can do nuclear fusion.
Yeah, so we base all of our approaches at fusion on this. That's a really good reason to care because most of the experiments that have been done for the last 50, 75 years have been utter abysmal failures. Uh, And so if we misunderstand how the star does it, then our approaches to it are going to be wrong. Why else would it matter? I went on like a big rant last time about sort of the metaphysical underpinnings of all of this. Why does it matter if we understand how the stars work? Why else? What about for just science in general? Yeah, remind me your name. Cecilia.
Not really sure how to word it, but
It's okay, dude.
to kind of make sure that it makes sense been right so far, so it like doesn't like so everything like makes sense.
So it makes sense. Yeah. I don't know about you guys, but I want to live in a world that makes sense. How about you? What happens if we live in a world that doesn't make sense?
It's annoying.
What if it's maybe worse than annoying? What's the worst case scenario for a world that doesn't make sense? Yeah. What happens? Yeah.
We die like the caveman.
Well, maybe we die. Yeah, maybe we kill ourselves somewhere or another. We forget to do something that keeps us alive. That's a serious risk. What else? What else happens? Yeah, Dante.
I want to counter die like the caveman because
Yeah.
we're not stupid.
Yeah, fair enough. Fair enough.
And to them the world made good enough sense.
Yeah. But a lot of cavemen did die. Actually, there was a ton of different hominid cavemen at some point, and we're the only ones left, so that's kind of interesting.
Yeah.
What else, though? Like, why? I don't know. This is actually super important, especially since you guys are not going to go out in the world and be scientists. A lot of you are going to go be teachers, though, so it's super important, actually, right? Who cares if, yeah.
One thing makes sense to the people that are like doing the science wrong, where like so confident like get answers. Like you were saying at past class, we like lose our ability to think if we just like follow whatever they say blindly to care like fact just very right.
Yeah. I mean, if you just take somebody's word for it with a lot of stuff, now it might not be stars, it might be something else, right? But if you get in the habit of taking people's word for things, maybe they stand to make some money by misleading you. Maybe they stand to take your stuff. I mean, it's been really gnarly in the past. People have pushed really bad ideas and really bad metaphysical philosophies in their own self-interests. And unfortunately, that's usually how the world is ruled. So keeping a good eye on how things are actually going down is super healthy for a civilization. Yeah.
A perfect example of this is 1940s Germany.
Yeah, yeah.
40s or 30s?
I mean,
Well, it started in the 30s.
yeah, Germany, I mean, Nazi Germany is an archetypical example. Communist, Stalinist Russia is a great example. Maoist China is maybe the best example. I mean, they killed, millions upon millions, tens of millions of people starved to death as the result of just kind of taking the great leaders' nonsensical ideas as salient. Yeah.
I'd like to posit most of Europe during the 1000s.
Yeah.
Basically all of it.
Yeah. How about the Dark Ages in Europe? Exactly. Yeah.
Take my word for it, bro.
Yeah. Take my word for it. We can't understand what you guys are saying in these ceremonies. Don't worry about it. Right? I don't understand what that math means. Don't worry about it. Right? So, okay. Anyways, just setting the stage. I'm going to keep asking you guys this at the beginning of class because it's really, I don't care if you remember any of this stuff 10 years from now, but this is something you should remember because you guys are all going to be voting members of society. You're all going to be participating, but you have to understand how the world works and you have to demand that it makes sense. All right, what else? Okay, so what else did we do last time other than reestablish this central crux, which we will continue to hammer home? What happened last time? Anybody remember? Been a long weekend. Yeah, what did we talk about?
We're talking about the history of the gaseous model of the sun and how we came to that conclusion.
We reviewed the history of the gaseous sun, and then we started into this idea about energy. And
Went on to different ideas they had. We ended just before we got into the one that ended up winning.
yeah, so we were right at the edge of talking about fusion. So we had to talk about this concept of energy. And to make sense of energy, well, because people were looking for a way to power the stars and they couldn't figure it out, right? So they're kind of thinking of ways to do that. And we had to talk a bit about what this word energy means, which is really important because there's this big equation, E equals mc squared, at the center of it, right? And so we had to talk a little bit about energy. We had to talk about what mass means. We had to talk about these concepts. What did I kind of leave you guys with as a good sort of street version of what energy means in the physics sense? Anybody remember?
Can you repeat the question?
Energy, what's it mean? Yeah, give it a shot.
I remember was it Aristotle the definition?
Aristotle did talk about it. Yeah, what did he say?
Just stuff activity.
Activity. Yeah, yeah. I think that's actually pretty close. Yeah. So in the terms of physics, it's we have material bodies doing stuff, right? That's really what it comes down to, and it's how much material is doing how much, right? So it's just material in motion, right? And we're quantifying that, how much material and how much motion. That's really what it comes down to. And there seems to be in the universe, maybe we don't have to go as big as the universe, but in this room, in a closed system of some sort, there seems to be a limited amount of material in motion. Like there's not going to be just a desk isn't just going to appear out of nowhere and start flying across the room, right? These are reasonable assumptions. And the amount of motion seems conserved too, right? If the desk is flying across the room because there already was one here and it crashes into a wall, then the wall is going to take up all of the momentum that the desk had when it was flying across the room. So this energy is a conserved idea, right? All right, so Einstein's E equals mc squared. Yeah, go ahead.
Electrical energy is just the movement of electrons.
Well, anybody remember anything about the material atomics lectures that I gave? We were talking about charge and all of this stuff. Yeah.
Isn't the electron just the surface of the atoms?
Yeah, I think that a material. I prefer a material representation of electricity. So electrons are weird because an electron, and this is probably kind of brings us up to where we stopped last time. We were talking about these particles and what the heck a particle was, right? So particles are kind of these bundles of measurements, right, that are predictable and replicable. So in some sense, the electron represents this set of properties that's measurable and conserved, right? But I think a much more sane and material and I dare say physical representation of the word electron just literally means a particular motion that the surface of the atom does. And that when you put two atoms together, the one that's doing more of that motion is capable of transmitting it to the next. Just like throwing your desk into the wall is going to take up the material in motion, right? It's going to feel that same transfer of energy. So, you could model electricity as your little measurement, your quantity of measurement moving down a wire, or you could think about the atoms doing something to each other, which I think is a little bit, it's a little bit more on the nose, and it works too. So the math can tell you either one. Cool. So particles. Wait, let's finish up this E equals mc squared thing. So I felt a little bit bad because last time I felt like I did a kind of crappy job of explaining this Einstein thing. So at the heart of the Einstein concept is this word mass, right? And I tried to kind of break down for you guys what this word mass could possibly mean, because it seems to be deeply confused with bodies themselves, right? You move a mass across the table. Well, that's kind of weird because mass is a property that you measure. Once again, we're swapping out properties for objects often in mathematical physics. It gets really, really confusing. And it actually does need to be fixed. This is another huge problem that we can teach an entire course about, similar to this problem with the stars. The reification of ideas into physical bodies is a huge, huge problem in physics, actually. Does anybody remember what that word reification means? That's a good one. Impress your friends with it.
Is it basically like the opposite of like an abstraction?
It's treating an abstraction as a concrete body, right? So it's a classical philosophical fallacy. It's not a logical induction that you can make, but the physicists have become extremely comfortable with it. And so these are two very good examples. Masses, electrons, they're both qualities, ideas, relational concepts that are being packaged as if they're physical bodies and moved around, right? You can't move ideas around is the problem. That doesn't make sense. Making sense is what this is all about. Like, I can't, I have a lot of love for my wife, right? But I can't just like toss it to the person at the back of the room, right? You can't move ideas around. It doesn't physically make sense. Things have to make sense, guys. This is your world that you're inheriting. There's a lot of stuff happening right now in the world that doesn't make sense, and it's not good. And as long as people are comfortable with things not making sense, it's not going to work out for most of us. Yes.
So, just go over what E equals mc squared.
Yeah, let's get there. Let's do that.
Yeah, it's energy equals mass times the speed of light squared, right? So your speed of light.
All right, so that equation, E equals mc squared, I'm not even going to bother writing it on the board because everybody's seen it in cartoons since they were 5 years old, probably. At the heart of that is an interesting idea. First of all, this is a special kind of energy that Einstein's talking about, and he's talking about the energy contained within these atomic systems themselves. So really within the atom, he's really speaking about these confined energy tied up in the atom. So some sort of freneticism in the atom itself. And it's quite interesting. This speed of light concept pops up all the time. Have we talked about the speed of light in this class at all?
A little bit, I think,
Not too much?
but we haven't gotten in detail.
All right, so last time we talked about the speed of light, we were probably talking about light, right?
Yeah, probably.
Probably. But it doesn't just apply to light, which is really quite interesting, actually. This was what was kind of blowing people's minds back in the 1800s. So electricity also travels at this speed limit, too. That's pretty weird, right? And it turns out all the little pieces and parts of the atom travel at this speed, too. So does anybody remember how I told you that I like to think about the speed of light? Why the heck does light have a speed limit at all? Anybody?
Because it's a communication between two atoms, and it's basically it's a wave in sense. So the material properties of the atom is the limiting is the thing that's limiting its speed.
Yeah, so all materials actually have speeds within them, which is kind of crazy, right? So I think that maybe I pointed out if I smash my hand on the table and put a microphone at the other end, it's going to take some characteristic time for the wave of that signal to reach the microphone at the other end of the table. And the reason for that is what? What specifies the speed of the material, the wave in the material? Yeah.
Its material properties.
Yeah, there's little subunits in here, and they have to get out of each other's ways. And some materials, the subunits move easier than others. So The only reason we have speed limits in any system physically is because of the subunit structure. So whatever it is, I like to model it as just the atom's structure itself, the material the atom's made out of. That thing is deforming during light. That same thing is deforming the surface of the electron, right? Sorry, the surface of the atom, the electron, in that electron motion, it's deforming at a fixed rate. So these atoms are all made out of the same stuff is what this is pointing out, and it has a fixed rate at which it can deform. That's the speed of light. So that speed of being able to bend something, the atom, is what we're talking about with this E equals mc squared business, is somehow related to the amount of material you have, which is approximated by this concept of mass, which we'll talk about in just a second, one more time to review. And the product of that is very much representative of how much material is in motion is possible in that atomic system. And so Einstein really cracked this open in terms of thinking about the atom as having internal motion to it. That's really what it comes down to. You realize that the atom had a tremendous amount of stuff moving around in it, and that we could maybe harness that, and this gets us off to the races with fusion. So before we get to fusion, yeah.
So remember, like a couple 2 weeks ago,
Yeah.
I asked you a question about the speed of light.
Yeah.
Is this a good time to answer it?
Heck yeah.
Okay, so I saw a documentary a couple years ago, or like many years ago, and it explained how a guy in the middle was like recording this guy around like the track. And if the guy around the track ran or went on the bicycle as fast as the speed of light, the guy in the middle would actually be older by the time the guy finishes doing the lap.
Yes, that's real. Yeah. So there's a lot of these there's a lot of these kind of mind games in the popular literature about the speed of light and in popular physics. Now, the reason that these kind of paradoxes crop up is because time itself is defined by the motion of some periodic system. Now, what is the fastest, most precise clocks that we can make? Anybody? They're called atomic clocks. And what is an atomic clock? An atomic clock, yeah, go ahead. What is it?
I was just gonna make a guess that it's like a clock that measures how time passes for an atom.
Well, it defines what time is, because in physics, time is what clocks do, okay? The most precise, fastest clocks that we can make are atoms that are giving off light at a really high frequency. They actually use these cesium atoms that are vibrating electromagnetically and giving off really high frequency light. Now, the limit of those oscillations, the limit of the actual propagation is still the speed of light, because the material can only deform so fast, right? So the problem is, if you make up an outrageous circumstance like, well, what if something could somehow deform the atom faster than the atom can deform? Well, the answer is you've kind of broken your clock at that point, right? You've really lost track of what you mean by time at that point. And so, I'm sorry to throw cold water on the time machine plans out there, but the reality is that time is simply what your clock is doing. If you break your clock, then you're unable to actually process what happens downstream of that. Yeah.
So why don't we use the atomic clock as our real clock?
We pretty much do at this point. Yeah. So we've actually redefined, and this actually gets us into a really interesting territory here with respect to the other particles too. We've actually defined a lot of these quantities, like the second, in terms of the number of oscillations of these atomic clocks at this point. So we do actually keep track of those things. Now, of course, we came up with the idea of the second because, why? Because it relates to the day, which is something here on Earth that works really nicely, right? It's of course in units of 60, which is totally insane. Did we talk about that in this class at all?
No.
Did it ever occur to you guys how freaking
About it last
Okay,
semester.
okay.
Wasn't it the Samaritans?
The Sumerians, yeah.
So
Yeah, so, you might have noticed that we work in base 10 for almost everything, right? Like decimal systems, $1, $100, whatever. But for some reason, time we do in 60, right? It's pretty weird, isn't it? So we inherited this from our deep intellectual ancestors, the Sumerians, right? Basically at the beginning of written history, out here in the West anyways. And yeah, so we've just inherited that mode. And so we translate the oscillations of that clock, that really precise clock, into seconds. And it is ostensibly a really good clock, but there are problems with clocks is the thing. So, you know, you guys might have heard, there's another experiment too. I don't know if this is the right time to do this, but let's just do it. It's kind of fun. So, you know, one of the predictions of relativity is that time, because time is defined as what clocks do in physics, that time's going to be affected by gravitational systems, right? And back in, I don't want to give a date to this because I don't know, but a while ago, several decades ago, somebody actually had a communications satellite in space that broke. And so it was supposed to be this nice geosynchronous orbit, just kind of flying around the Earth. And one of its thrusters broke or something, and it started doing this really elliptical orbit, right? Like real elongated orbit. And what they noticed was that every time the clock came in to the Earth, its timekeeping actually changed as a result of it. So that was weird. It actually seemed to slow down a little bit, the clock. And people were like, oh my goodness, time slows down in gravitational systems, right? But again, nobody wants to talk about the fact that time is defined as what your clock did. Now, does it make sense? Is there a reasonable explanation for why a clock would slow down in a gravitational system? Sure there is. Think about it. Clocks are made out of atoms, right? So let's do another experiment. Let's say I keep time with how about like a grandma clock, one of those grandmother clocks? You guys ever have one of those when you're growing up? They dong all night long and everything. Yeah, my wife's parents have one of these things. It's just hilarious. Let's say you take that thing up to space. What's going to happen? It's going to tell you time stopped, actually. It's not going to work anymore. It's going to actually slow down. The pendulum's going to slow down the further you get until it just stops. Yeah.
This was such a problem for the for one, this is why we have time zones, and it's part of an inheritance we took from the European sailors during the 1600s, mainly the Spaniards and the Dutch, because what they found was that it was really hard to keep touch of what the date was, what the time was, because the clocks kept degrading. Like the time would degrade. They would lose hours, they would lose days because the clock's material degraded significantly faster on the ship, and also it was inaccurate given the grandfather clocks were just super inaccurate on the open seas.
They're also really affected by gravity, is my point, right?
And so they created a different clock that was less affected by it, and suddenly they had way more hours.
All clocks are affected by gravity, though. That's the horrible thing about gravity. Now, why in the world would gravity affect clocks, though? Let's make sure that this makes sense to you, Owen, because I want to make this make sense to you. So, what the heck is gravity? I think we've played with this a little bit, but I think it's really important that we deal with it. You know. So this kind of brings us to this thing, which I did a really poor job explaining. So I want to make sure I nail it today. I went home and I felt really bad because I felt like I didn't get this across. Sorry, you had your hand up, Kevin.
I was just gonna say, does it have to do with how gravity affects atoms?
Yeah, well, yeah. Let's just assume we're all made out of atoms and everything else is in general too. And the atoms are made out of something else too. There's some sort of subunit structure to the atoms themselves, but we won't even bother with that at this point. So what is gravity? What's going on with gravity? So last time I talked to you guys, I told you that this thing that Einstein's actually most famous for is not the thing that he actually got the Nobel Prize for or anything like that. It's for this processing mathematically this equivalence principle, basically recognizing that inertia and gravity pointed at the same definition of mass, whatever that was. And you could set these equations together, do a bunch of high-level math, and come up with another set of functions that actually gives you highly predictable outcomes for how bodies move in gravitational systems. This is the basic idea, right? This illustrates this equivalence thing, right? So if you're inside of a rocket ship and it takes off, what do you feel beneath your feet? It basically feels like gravity, right? You can't see out the windows, by the way, so you don't know what's going on. But you can feel this in an elevator sometimes too. When it goes up, you feel like you get heavier, right? Mm-hmm. The same thing could be true if you're in a room with no walls. It feels exactly as if you're on the rocket ship and it's taking off too. The gravity feels just like...
You mean no windows?
No windows, sorry. Right? So this is kind of one of these famous moments. I don't know if it even ever happened or what, but Einstein supposedly had this daydream where he realized that, oh my goodness, you would not be able to tell the difference between gravity and inertia, right? Which points almost more interestingly to me at a shared definition of what mass could mean, right? Because mass is in both of these equations. It's the shared feature that allows you to actually create general relativity at the end of the day, which is far beyond the scope of this course. So what the heck is gravity, inertia, and mass? How does mass relate to these and so forth, right? Does anybody remember what I threw out there last time? Or maybe several times now? Yeah.
Is part of it the collective influence of a group of atoms?
It is. But in what way? What does it mean that you're sticking to the floor right now? Well, how about this? What does it mean if you have a Velcro something stuck to another piece of Velcro? They're hooks. They're hooked together. They're attached to each other, right? It certainly seems like both of these experiments point to the shared reality, which is that the atoms are stuck to their surroundings. They're physically entangled. Maybe that's not the right word to use because that has other meanings. They're physically attached to their surroundings, right? And that attachment thins, their ability, their connectivity to their surroundings thins the further they are away from one another, right? Okay. So this is actually really phenomenal. So the reason that things stay put is because they're attached to their surroundings. The reason that things are attracted to large bodies is because as they move, they're increasingly attracted to their surroundings. And so, mass. Does this make sense? Okay, that's good. All right, so this kind of brings us up to where we were last time, which is we were talking about the atom, and we were talking about this particle soup that the textbook uses to explain fusion, right? Because we're going to look at fusion really quickly, and your textbook goes through it and probably asks you a bunch of questions about the equations for it. So here's the equations. We'll come back to these in a second, but they involve a bunch of little pieces of the puzzle, right? What are these little numbers in front of the atomic names? Does anybody remember? Yeah. Why do they have different numbers? Like, what's a helium-3 versus helium-4?
I believe that's the number of, protons and neutrons in the nucleus?
Neutrons, yeah. Neutrons makes the difference, right? So what the heck is a neutron, though, is the problem, right? And we got all these other things, right? We've been talking about these things, electrons and whatever. What does it mean? Like, I've been basically arguing to you guys that these things can't possibly be material bodies because they occupy no volume whatsoever. They're literally just points. And if that's not enough to convince you, they actually have time components to them, right? They have motion inherent in them. And obviously, material bodies don't have motion inherent in them. You don't need me to tell you how this desk is moving to understand what a desk is, right? So what are they? That's a really interesting question. What the heck are these things? We talked about the electron. The proton, we can think of it very similarly to the electron. It's sort of, as the atom actually goes through this motion that it does with the electron, the interior is also undergoing a motion which is equal and opposite. Now, how in the world do they get these, and we'll come back to the neutron, how in the world do they get these mass thingies, though? This is where it gets really bizarre, right? You might think, does somebody like take, how do you have a motion? I'm telling you that an electron is the motion of the surface of an atom. How does that have mass to it? How in the world do they get this? This gets really, really bizarre, actually. Any ideas? Yeah.
Is it some odd, like, we add a chemical and see how it reacts, and then it's the size of the reaction dictates its mass?
A little bit, yeah.
All right.
A little bit, yeah. Actually, what they do is they basically see how much how strong of a magnet they need to deflect some electricity inside of a vacuum tube, right? So basically evacuate as many atoms from this tube as possible, drive a current through it, which we could model as just lining up all of the remaining atoms that are in it so that their shells are conducting to one another. By the way, atoms, when they're in a vacuum, this is insane. They get huge, actually. They get enormous when they're depressurized. Their shells, when they're knocking around in a really pressurized environment like this room, doesn't feel that pressurized, but we have a lot of pressure here, actually. There's a ton of atoms just flying around between us. But when you depressurize an atom, it gets huge. All right, so anyways, there's this column of atoms. We could just think of it as like that single file wire that I was showing you guys a few times back. And they see how big of a magnet is necessary to deflect that column of atoms, right? This is where it gets really weird. They think in their minds that since they've already decided this is just a little particle of electricity flying around, that the only thing that's holding it in place is its inertia, right? Inertia involves the concept of mass. And so therefore, the moving electrical particles must have mass too, and deflecting them will tell you how strong that mass is, right? So what's my point? My point is that this isn't exactly the same kind of mass that you would find when you weighed yourself on a scale or something like that, right? This is the equivalent magnetic deflection of a current carrying column of atoms, essentially. That's what we're actually talking about. Does it make sense? Okay, so we got all these particles, right? We got all of these attributes that we can measure. Neutron, that's a weird one, yeah.
So the mass was like it was like a number that they came up with to answer the question they made themselves.
Yeah, they basically say, how much effort does it take to push this column of electrified ionized atoms in this vacuum tube, right? These are called cathode rays. When I was a kid, all the TVs were cathode ray tubes. So they just have these big tubes, and they have these big columns of ionized atoms in there, and they actually write screens, like all of the original computer screens are like this and stuff, right? So they say, how big of a magnet, how strong of a magnet do I need to push this thing around, right?
I've never felt. Someone explain.
Yeah, I've seen it all. You saw some cathode ray tubes? Is that what you're saying?
I grew up with CRT.
You grew up with them, yeah. They're kind of fun. Yeah. So the real confusion here, I hope this answers your question, Dante. The real confusion is that you are mistaking the tension in that column of ionized atoms for the actual weight of those atoms. So think of it this way. You guys ever play, who plays guitar here? Anybody? Nice, a bunch of you, yeah. I play a ton of guitars. So you ever pick up a guitar string? It weighs like nothing, right?
Oh.
But then you tension it on the guitar string. So you could also, anybody shoot bows and arrows too? Yeah, all right, same people. Same thing, right? Bowstring weighs nothing. You tension it up to like 40, 80 pounds. It's really hard to displace, actually, once it's tensioned, right? I would posit that that's sort of what's happening in these vacuum tubes, in these cathode ray tubes as well, is that you have a tensioned column of atoms, and that displacing it does require some effort, but it's not the same as gravitational mass. It's not the inertia. It's not its connectivity to its surroundings that's making it really hard to move in the same way that your body is hard to move around the room. It's actually this local tensile network, yeah.
So I was thinking as well of like dead weights versus cables, where like just by increasing the tension on a pretty light, it could be a pretty light cable, you can get it to feel as heavy as just a 15 kilogram thing of steel.
Yeah, tension's crazy. It's utterly neglected at the atomic scale. Yeah.
So a better word there for mass would be like the internal tension.
Yeah, I mean, you'd have to really reevaluate what's being measured in these experiments, because it's an equivalent electromagnetic force that's being converted into kilograms, which is very bizarre, right? Okay, so my point is not to redraw this table, so
Let's explain why the mass is so.
Yeah,
the atom itself.
it gets really weird, and then the proton itself gets really weird too, because what is an atom? How do you actually look at a proton without how do you look at an atom without an electron shell? Well, obviously you can't. So we're actually talking in some sense about an ionized atom in that sense, something that has been really charged up. And we're talking about a positively charged hydrogen atom in that case. I mean, the chemists actually, this is all, anybody do chemistry here? Anybody? No? Yeah, I mean, every once in a while I have a chemist in here. Chemists actually call hydrogens protons, which is really funny, because they think of the positively charged hydrogen. So the word proton is broken in a very different way. What's up with neutrons, though? Those things are crazy. So what is a neutron? Because we have neutrinos up there too. We'll deal with those. What's up with neutrons? Yeah.
Just like the sun. That charge.
Yeah, that's right. Yeah. So it's somehow well, how do we even know there's neutrons? First of all, that's kind of weird. So people basically started realizing that, it would have been really nice if this periodic table, if each atom just kind of went up by one hydrogen. And they almost do, actually, which is really interesting. So some of the early chemists thought, oh, the atoms are just kind of built out of hydrogens. You just smash hydrogens and cram another hydrogen on, and you get a bigger atom. And it almost works out, but it doesn't quite work out, because each type of atom, like a calcium or an oxygen or something, it has actually a distribution of weights to it, of masses to it, right? So the idea for the neutron was proposed, which is sort of this particle that wouldn't show up in terms of really changing the actual outer structure, the electron shell of the atom necessarily, but it would add mass to it. And then later, actually, when people started breaking atoms apart, they started realizing that these neutrons could be detected. But what's really weird about neutrons is kind of interesting, actually. So a neutron, by the way, how much does it weigh?
Apparently slightly more.
This is kind of hard because we got scientific notation here. How about if I told you that the proton weighs almost the entirety of the atom itself? And by the way, these are just deflection equivalents, so I wouldn't put too much stock in them. But it's interesting, right? So the electron weighs almost nothing, mass-wise. Its mass is almost nothing. Proton is most of the atom. The neutron's what? Almost exactly the same, it turns out, right? So this is what's really cool. If you actually have a radioactive atom and it decays, it might give off some neutrons, right? What happens to those neutrons? They only live for like 15 minutes. Guess what happens when they decay? What do they decay into? Yeah.
Energy?
Radiation?
A little bit, all these things in some sense. So actually when they decay into a proton, an electron, and a little bit of zip left over, a little bit of energy called a neutrino. So that makes our list finally, right? So that's interesting. A proton and an electron, what happens if you stick a proton and an electron together, according to the good old model of the atom? Right?
An atom.
You get a hydrogen atom. So a neutron is basically a hydrogen atom that has no charge yet. And then when it actually decays into a charged hydrogen atom, or one capable of being charged at least, then it loses a little bit of zip doing it, which is this radiation given off called the neutrino. So anyways, okay, questions over this before we actually look at it? Yeah, yes, both of you guys.
What's a neutrino?
The neutrino is actually that extra radiation that's left over when the neutron decays into the hydrogen.
Okay, just a little bit of energy.
Yeah.
So a neutrino is just energy left over, or
Some sort of material, it's obviously energy is material in motion, but it's some sort of radiation that emanates during that restructuring of the neutron into a hydrogen. So when it goes from being this electrically inactive atom called a neutron to being an electrically active atom called a hydrogen that can actually participate in electrical processes, light and electricity, then it actually loses a little bit of motion into the system. The whole network absorbs it as radiation. So just like light is just some motion being lost into the network, right? Some motion that the atoms in the light are dissipating into my eyeballs. The same thing is true with the neutrino. Can be thought of very similarly.
so how does it have mass?
There's massive energy.
Yeah, again, this is often done via conversion, right? Once you kind of drink the Kool-Aid that the actual deflection forces of these electrical deflections by magnets is the same as inertial mass, then you start tacking masses onto everything, and it gets really far away from the original meaning of the word mass. Yeah.
If radiation can be that small, what is radiation?
You mean that weak? Is that what you mean?
That we get.
Yeah, yeah. Well, radiation is really just a particular like electromagnetic it's really just an oscillation that's given off into the environment by the atoms. So I've modeled the atoms many times for you guys as basically these furry structures, right? They have, a true shell to them, let's say, but they also have a kind of furry part that kind of carries the vibrations outward from them, right? And so radiation, technically that word's enormous. I had a physicist tell me the other day that sound could be considered a kind of radiation, and I see what he's talking about. But what I mean is electromagnetic radiation, right? So I mean this particular dance that the surface of the atom does during this light relay, right? And the neutrino is a very particular form of that. It happens to be a really, really penetrating radiation, right? It really gets relayed from one atom to the next almost perfectly losslessly. So it can travel, maybe through half the Earth or something like that, one atom to the next without decaying. The radiation is super, super intense, actually. Yeah.
So when people generally refer to like just radiation or nuclear radiation, they're referring to electromagnetic.
Yeah. Yeah. Yeah.
Okay.
Yeah.
Because there's thermal radiation.
Yeah, yeah. I mean, radiation, like as a concept, like you almost want to like look at this non-physically, but it just means something moving away from a point source, right? And so we're talking about these various.
Something radiating.
Yeah, so like when I lived in New York, we had radiators on the wall, right? Which are just they're giving off heat into the room. It's
a radiator in your car.
Or radiator in your car, right? It's kind of same thing, right? The other way around. So. Okay, so these are all the little bits and pieces. Now, obviously the atom can't be made out of all these qualities, but that's the atom that we get, not the one that we want necessarily. Yeah.
Well, radiator is called such because the heat is pulled into the whole radiator, and then it radiates that heat out into the air.
Yeah, fair enough. That's true. That's a good way of looking at it. All right, so these are the equations for the proton-proton chain reaction that's proposed. This has actually been a standing proposal for quite a long time in our sun. Now, this is thought to happen in basically run-of-the-mill stars, kind of like our star, and we'll sort of look in a moment at our star compared to other stars. But this is pretty simple. You got regular old hydrogens; they're getting squished together, and they give us a bigger hydrogen, right? Weighs more. You also get an electron and it's a neutrino. Then those guys can combine in certain ways by getting crushed together, and you get a helium, which is actually the next biggest atom up, and a little bit of light out of it. That light, by the way, is proposed to be the light that bounces around for millions of years and finally comes out at all the right frequencies to give us our nice Planckian black body spectrum. And then some of those guys can combine eventually and make a big old helium, a helium-4, and they kick back a few protons, which can then cycle around, right? They can cycle around and repeat the whole process. So energetically speaking, no issues with this equation. It's fine. The main difference that we might want to consider is that in a gaseous sun, how does this happen? Where does it happen? Where does it happen? Let's start there. Yeah.
At the core.
In the center. The center is the only place in this ball of gas where there should be enough pressure to squeeze these atoms together, right? And pressure, of course, is going to give us temperature, right? Pressure is proportional to temperature. So how much temperature are we talking about? Do we need for this to happen in a gaseous model? A lot. So about 12 million Kelvin, right? So that's 12 with 6 zeros after it, Kelvin, which is, close enough to Celsius for jazz, if you can think about it that way. Really hot. And this is the kind of approach that people are using on Earth. They're trying to do the same thing with their fusion reactors. They're trying to take this really, really, really hot gas and confine it with magnets and hopefully get them to all stay in their same place long enough for the atoms to stick together. And they do occasionally actually stick together. It's just extremely inefficient and really, really hard to hold those atoms in place when they're that hot.
They almost always just destroy themselves immediately and
Yeah.
basically just cease to be as complete atoms.
It's really hard to keep that plasma coherent to pull this off. Okay, so
Kind of makes sense for the reals of it.
and there's other problems with this too, right? What keeps the atoms in the center of the star in this gaseous thing? It doesn't really, if the sun doesn't have a surface, what's the container that's holding this gas inside of it? It's very unclear. It's very strange, actually. So
I will just turn gravity shoved at my face. It's gravity or
yeah, it's always gravity. In this case, it's supposed to be gravity itself, right? But it's weird though, because gases are collisional by definition, so they should be bouncing off in every direction. I mean, this is very strange too. I could cite some other pieces that are weird about this puzzle, like these huge nebulas we see in space. Almost none of them are actually gravitationally bound. In other words, they're all just sort of dissipating, right? Which is what we would expect gases to do in a vacuum. So the idea that they would just sort of fall in on themselves is actually pretty bizarre on its face. Anyways, that's the sun that we have, maybe not the one we want. So yeah, so I probably should have pulled this picture up. Everything's supposed to be happening in the center of it, because that's the only place that fusion can happen inside of these stars. Now, what about in the liquid sun? If in a liquid, what do we have? What chances do we have? Yeah?
Can it fuse anywhere?
Yeah, so the basic idea in the liquid is that there's layers, right? This is like a graphite-like layering structure with this hydrogen, right? And so you have, and we use these to explain sunspots as well, is the kind of burping up of these impurities that are inside of it. But in addition to heavy impurities or gas bubbles or things like that, you can also theoretically trap these individual hydrogens in between the layers. And then what? You have the entire tension of the whole system, the whole gravity of the whole system squishing it together. Now, this isn't just a theoretical idea, though, either, which is really interesting. So actually, a team at NASA did a version of this. They did it actually in a solid metal, though, instead. So what they did is they impregnate this solid metal with a bunch of hydrogen, heavy hydrogen gas, basically. So it sops it up like a sponge. And then they apply this really fast laser pulse to the little brick of metal, which causes it to kind of contract really fast. It shocks it really fast, gets really hot, shocks it. And they do fusion with this. They actually get the same fuel densities that those guys are getting in the huge fusion reactors in this little piece of metal, just by squishing it the same way. So this is called lattice-confined fusion. It's a legitimate approach to fusion. Now, the problem with doing lattice confined or lattice confinement fusion, sometimes written. It's actually really interesting stuff. So, this stuff is actually being employed for, not for energy purposes, but for the generation of neutrons, which are useful in medical procedures, things like that, where you need to have neutron sources on demand for imaging and stuff. So lattice confinement fusion is actually really, really interesting. So in a liquid star, you actually have the ability to do fusion everywhere, not just in the core, everywhere. Now, why is that interesting? Or why should we believe that's even possible? It's a couple examples of that. Well, let me say this first. This hasn't been optimized in terms of being able to generate the kinds of powers that we see on the star. So if we wanted to even do this kind of lattice confinement fusion naturally, what's the huge advantage that the star has compared to our laboratory? Yeah.
It's massive.
It's huge. It is so, so, so big. And all of those atoms are all working towards squishing whatever's stuck between the layers of its lattice, right? So this is one of the reasons that I'm a little bit pessimistic about the liquid sun revolution necessarily solving all of our energy problems overnight. I don't know how to do that. I do know that if we can find a passive source of pressure, and I've been, pestering my engineering friends with ideas about this, that we might be able to pull it off. But we certainly aren't going to pull it off with these giant gas reactors because, this just seems like a fool's errand too. So fusion, I don't know. I can't guarantee you that it's going to be the way that we power our civilization in the future. Yeah.
Also a bit pessimistic, but I don't think the government's going to be very happy about a cheaper attempt at fusion.
Well, the energy companies might not be. Yeah.
Well, because because all of the hadron colliders are mostly funded by the governments, and it's like it's their reason for why they're not doing nuclear.
Yeah.
It's like, well, we have a better solution.
Yeah.
Wait, guys.
Yeah.
Just wait a few more.
Yeah. Well, yeah. So the only thing, maybe I don't totally understand. I guess what I'm trying to tell you is I don't know how you scale up the work done in this paper to something that's a full-on fusion reactor, but I'm not an engineer. Maybe somebody's figured it out. And I would say that the only thing, that there is a little piece of this puzzle that makes me think maybe somebody is figuring it out, which is that getting the interview with the guy who was at the head of this paper was one of the most difficult interviews I've ever tried to get in my entire career. I mean, the level of NASA bureaucrats who just kept getting in my way trying to talk to this guy was unbelievable. So kind of made me feel like they were onto something and they didn't really want to talk about it. I did eventually end up, he left NASA and I was able to get in touch with him many years later. But it was very, very difficult. And the NASA people still stepped in all the time. And it's very, 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 very weird. So I don't know, maybe fusion, maybe lattice confinement fusion is really promising. I like to think that it would be. I don't know how personally to implement it, but that's okay. Now, why do I think that stars might be doing this? Right? So yeah, it has a theoretical basis in the liquid sun, and we've talked about all these reasons why the sun doesn't really seem like it's a gas, but why would I think that stars are doing this instead of just doing it in their core? There's a couple of examples. This is my favorite one, though, actually. It's called Cebulski's star. So Cebulski's star is a really, it's a well-studied star that people found in its atmosphere, and we're going to talk about how this is done, but I think we mentioned it maybe the first week, that when you look at the sun, for instance, you see its nice rainbow of continuous color, right, from the heated surface. You also see little lines overlaid on it, right, which represent the individual ions, the individual atoms in the atmosphere, right, the gases in the atmosphere. They give us lines, right? This star has really, really weird lines in its atmosphere. And there's probably many other stars like this, but this is the best studied of it. It has lines in its atmosphere of elements that should only last for about 15 minutes. Heavy elements, really big metals that should only survive for about 15 minutes. So sometimes when you make some of these really big atoms at the bottom of the periodic table, we can make them in the laboratory through all sorts of processes. Mostly really short-lived fusion type of things, or fission ones where they fall apart into these things. But they don't last very long. The big atoms tend to fall apart. They're kind of like bubbles that want to pop. So how in the world is there an atom that should only survive for 15 minutes, a huge atom, in the atmosphere of this star? That's pretty weird if it had to come from the center of the star, and that's the only place where fusion. Furthermore, I don't know if anybody noticed, but what was the biggest atom that we got out of our star? Our sun.
Helium.
Helium. That's the second, that's number 2. I wish I could pull this thing up. Helium's number 2 at the top of this thing, right?
Yep.
It's a really little atom, right? So most of the stars are not much bigger than us. Most of them are smaller, actually. And there's only a few of them, the big ones, that give us bigger stuff. And we're going to talk about the differences and how that works. And to make the really big atoms, you actually technically, according to the standard model, you need a supernova to generate the kind of pressures. You need to explode the star and have it have these insane compression shock waves to actually get the fusion to go down to make these big things. So how in the world do you get some of the biggest atoms, these enormous metals, in the atmosphere of this star if it's doing it in the core, or it comes from supernovas? Yeah.
I just immediately had a question pop in my head when you said that those heavy elements could only happen we have them in a supernova.
We got a lot in our atmosphere too, by the way. Just
How do we produce them in labs on Earth, and then say they can only be in super? I'm just. Confused.
I think that we make those ones by fission. So we have even bigger atoms and we break them in half.
How do we? So we just find a bigger atom? Okay.
Yeah, we do. We have some big ones on Earth, which is really interesting too on its own face. Where do these things come from? If they have to come from supernovas and stuff, this gets into a really epicyclic story, actually. Yeah.
Would it be that there's just another class of stars that's like super dense that are in the mate sequence, or are dying off?
Well, no size of star is capable of making an element that big. No stars. The only gaseous process that can do it is a supernova.
Well, assuming it's liquid.
Assuming it's a gas. But assuming it's a liquid?
Assuming it's a liquid.
Assuming it's a liquid, all the stars can make all the elements, no problem.
Okay.
That's the main difference, right? Now, we have a lot of big metals in our star's atmosphere too. So we see all these really interesting lines. Most of these elements we can see actually in our star. The story is, of course, that that the star got them from supernovas in the past from somebody else, basically. The star is a multi-generational star. It's eaten all this stuff from other people, yeah.
Well, could you explain how a star being liquid gives it the ability to create any host of elements?
Yeah, so the idea is that this hydrogen liquid, is in this metallic state that's very much like graphite.
Okay.
So it has these layers to it. Water actually does this too. Most people don't know that, but water actually forms these hexagonal layers as well. And the idea is that there's a lot of both tension amongst the layers and compressive force literally from the gravity throughout the star as well. So we're kind of overlapping on this gravitational business. But we have a way to confine those individual atoms in between the layers now. So you can actually imagine them through there's all sorts of energetic processes happening in the star, right? There's convection we talked about. There's these crazy flares that happen, where these collisions happen between the material at the surface, and you get these eruptions and all this stuff, super energetic, compressive processes. So you're basically smashing together whatever impurities are inside of that thing to begin with. And you have the opportunity to generate all the force you need to pull off any fusion reaction, essentially. And you don't have to be at the center of the star with gazillions of degrees. You basically have a uniform density of the star throughout. Keep going.
So given that our star has majority hydrogen, helium, and some metallic elements in its atmosphere, would that indicate that it's more likely to be in a gaseous state?
Why would you think that?
Well, given
that it doesn't make more of the heavy stuff, is that what you're saying? I see. I think that might just be a mass-based thing. Yeah, I mean, it doesn't. It's a pretty little star. We're gonna start seeing there's some ginormous stars out there. So, and also estimating the size of stars gets really, really weird. It's actually kind of fun. So, we'll deal with that in a second too, or at some point in the next couple of weeks. Now the question remains: are the heavy things that we do see in our sun's atmosphere, are those being made by our star, or are they just leftovers from some bigger star? That's a hard question to separate out. But we have the possibility of doing it, at least, with the liquid sun, that we don't even have the possibility of doing with the gaseous sun. Yeah.
Would it be both?
What do you mean?
Could there be some heavy elements that are there because of a
Oh.
supernova, but some of them that it did produce itself?
Yeah, absolutely. I actually think like almost all, whenever you have competing mechanisms, there's often a happy medium between the two. So yeah, it could be. I mean, the sun's eating stuff all the time, right? I mean, presumably it's eating asteroids. Maybe it's even eaten some planets already. I mean, these are pretty standard mechanisms for the planetary scientists when they talk about the history of the solar system.
Those are gluttons.
Yeah, they're hungry. They got a lot of pull. And so, yeah, maybe it's a little bit of both. We don't know. But I do know that with Cebulski's star, it's very difficult to explain that the thing ate something, right? It's funny because if you go to the Wikipedia page for Cebulski's star, and you should do this, the standard explanation given by the astronomers for this phenomenon, what do you think it is?
It eats stuff.
The aliens are dumping their trash there.
Really?
I'm serious.
I mean, they would make a great trash disposal.
Well, it's like, it might be, maybe, it's possible, but I mean,
It's the most unlikely thing I've heard.
yeah, I mean, I'm one of the most open-minded people. I'm also extremely disagreeable, so I don't know. I mean, maybe, yeah.
I want to ask, is it Cebulski's star?
Cebulski.
If you can go to the photo of it.
Yep.
I wanted to ask what's up with the lines on it being so pronounced in that photo.
Lens glare, I guess. Yeah, lens flare, is that the word for it? I mean, here's the funny fact too, by the way, because we're about to start we're gonna get into it thick about this, because saying something about a point of light in the sky turns out to be way more difficult. So, can you measure the radius of a star with like a ruler or something?
Probably not.
Probably not. Not accurately.
No, you can't actually measure the angle. So the optical angle, right? You can't do that with stars, right? Because depending on how far or close it is, it just looks bigger or smaller. Maybe it's brighter. You can't tell. You really cannot tell. You can't measure the actual angle like you can with a planet, right? It doesn't have an obvious surface that you can see. So it's very, very tricky. So whenever we see these pictures of stars and stuff, they're always exposed to whatever limit they want to get the photograph that they have. Coming up with the actual radius of the star is a super tricky business, actually. Yeah.
Even if they're liquid stars, it's still like even in the sky, they still wouldn't have like any real apparent surface because they're just like overexposed.
Yeah, and they're covered in this really luminous gaseous atmosphere, right? I mean, our star it's insane. Like the corona will blind your eyes out. It's very, very hard, which makes taking a picture of the surface really, really hard, which is what we've been working on in the background this last couple of weeks, right? It's very tricky. Yeah.
How do stars determine what is impurities to put out into sunspots? It's like,
That's a great question. Yeah. I mean,
theoretically, there shouldn't be any discrimination if it is a liquid sun and it can fuse all the elements. What is an impurity?
I can answer that question.
oh, cool.
Impurity is basically anything that isn't what the majority is. So if the majority of, let's say you melt a block of steel or iron more simply, right? You melt iron and then you get some metals in there you just melted it. No other didn't put any extra metal in there. You get some metal that isn't iron in the melted iron. That's impurities because it's not what the majority of the block was that you melted.
And through convective processes you can separate it out, right, as slag, right?
When you melt it, it's just when you melt it and turns to liquid, the impurity is because the majority is one, generally homogeneous atom. The rest of it will just be pushed out because it's not the same.
Yeah, it gets kind of squeezed out. It's kind of interesting.
You see the same with water and like
So the impurities, yeah, with water, by the way, it could be a gas phase that's separating out too, right? So you could have expansions that result, right? There could be gases that are essentially evaporating in the interior that bubble up, right? So we see this when you boil water, right? What are those little bubbles that come up?
Steam.
What's steam? Just-
Water that's been turned into a gaseous.
Yeah, it's just gaseous water, right? So, you know, in some sense, that's an impurity that's being excluded along density and gravitational gradients from your water in your boiling pot, right? So, I mean, look, the details of this are extremely underdeveloped. I mean, this is the kind of work that people will be doing for the next 500 years after this renaissance occurs. And if it does happen, which I personally have tried to make a case for you that it is happening in your lifetime, it'll be wild. But these are the kinds of problems that people will be tasked with, because the ones that are supposed to be solved in your textbook will no longer apply. So all this work has to be done. And you know, I can't promise you that we're going to have fusion reactors anytime soon as a result of it, but it won't hurt, that's for sure, to understand at least how the stars do it. All right, so questions about fusion before we move on to stars in general and trying to tell a story about stars in general. You follow all this? Yeah.
if when you feel I'm trying to figure out how to phrase this question. How much more energy is produced from an equivalent from a fusion, like from two hydrogen coming together rather than like one hydrogen splitting?
That's a great question. I don't know the answer to that. It's a really good question. I have to look that up. It's not great. It's not a lot of heat that you get back from these fusion reactions, which is part of the reason why these reactors have been so inefficient, right? Like, I guess,
Liquid model.
what's that?
I meant like
Either way, fusion, like these, the equations that I showed you, they work in either case, right? Yeah. So, the difference, actually, the main difference is that in the liquid sun, that little gamma signal, which is our light, it doesn't have to bounce around inside of the sun for millions of years as the liquid. It literally is just absorbed. That energy is actually absorbed and thermalized by that lattice, which then is emitted at the surface as a black body, because it's just heat, essentially. So the gamma kind of turns into heat. I mean, the equations might change radically. I have no idea, honestly. But the amount of heat that you get out of, or let's say light energy or whatever, it's not great from fusion. This is one little thing that I'm a little bit, I don't know. I don't like to oversell the promise of fusion as the result of this renaissance. I'm not sure that's the most meaningful piece of what's going to happen. I'm slightly afraid that the sun can pull it off because it's huge. And we might have a hard time pulling it off because we need a high pressure gradient to pull it off, or a high tension system to squeeze things together between a layer, right? Like pulling together two tight rubber bands together. We need something that generates passive work. That's how we get all of our energy in the world, essentially, is we find these passive flows, right? We build dams against water, right? We burn things.
It's turbines all the way.
It's turbines everywhere. Even your body's got turbines to make little ATPs, right?
Mitochondria is just a turbine.
And it's inserted itself between the food and the air to make this electrical conduit. So, you know, we have to find a pressure gradient, even if we nail this fusion thing. And I don't know what that is yet, so, but maybe NASA people do. All right, so where we're going next is we're going to try to make a map of how all of these different types of stars relate to each other. So when we actually go back and look at the night sky, we actually see all sorts of different stars. And roughly speaking...
That is not to scale, is it?
No, this is not to scale. But it kind of gets the point across, right? There's different looking stars, all right? So they look different. Some of them are brighter. They're different colors. I probably should ask you guys, what's the difference between all of these? These white dwarf ones, for instance, that's a huge, interesting story we're gonna get to, but they're really, really bright and they're really, really little, or are they? I don't know. They're really, really bright in terms of temperature. And they're very hot, but they're really, really dim in terms of the actual magnitude of their signal. So that's weird. Yellow guys like us, who are pretty familiar with, have been talking about one of those this whole time. Most of the stars are smaller than us. They're these little cold dwarf stars, red dwarfs, right? And then we got some bigger ones. We got ones that are blue. They're super hot, right? So how do we put these all into a story of where they all come from? That's really where we go next. Now, we of course have two totally different stories to tell, depending on which type of star we embody. But we can start to classify them, because I think the classification, this is just sort of like taxonomy, right? You guys know what taxonomy is? You just sort of like see the relatedness amongst animals, right? And like, oh, this one's got flippers, that one's got flippers, they must be related somehow. So we're going to try to make some sort of a little map first of all of these before we even try to compare the stories of them. Now, the annoying thing is that there's a few of these guys that don't fit nicely into our map, right? There's always the platypus and the dodo or whatever that don't quite fit into your map, and you got to come up with a more interesting story. So the first thing we've talked about a million times is the temperature thing, right? That's a pretty obvious piece of the puzzle. So we know that as things get hotter, what color do they change towards? Heated bodies in the laboratory. You guys have all seen this before, yeah.
They shift towards the ultraviolet range.
Yeah, they get blue.
Typically ending up with their peak in the visible range.
Yeah, but in the blue, right, they're bluer. So things that are cooling off, they get redder, right? So that's nice.
Yeah,
So
it's more higher. This blue is higher energy than the red is lower energy.
yeah, you can see these temperatures sort of this peak. It's called the wine peak. It actually shifts a little bit into the redder side of things, right? As the thing cools off. So that's nice. That's the easiest piece of the puzzle that we can quite easily do, which is actually classify these stars according to their apparent temperature. This is literally just looking at the black body from the surface and mapping it onto a temperature that corresponds to the way that this peak shifts.
I want to point out that even though the sun is highlighter yellow there,
Yeah,
if the sun will always appear pure white to you
it's true.
in space.
It is true.
It's the
Not
focus
most
point.
stars.
That has more to do with how we've defined the word white, though.
Not actually. A lot of stars, even if you look at the night sky a lot, you can tell they're red ones.
Well, actually, have you guys, anybody ever played with a telescope looking at stars before? What did you notice? They look like different colors to you?
Yes.
One thing that's really cool, if you ever, like, that I really noticed was that as you adjust the focal length, they kind of, do this kaleidoscopic thing. But what's really interesting is that each star's kaleidoscope is like a fingerprint. It's very different, actually, because you're seeing all of those individual little differences in their atmosphere, right? All the different elements, the different atoms, they all have actually different color spectrums to them. And as you tune the focal length, you're actually refracting it away. And you can actually separate all the colors out. And so, you spend some time with a telescope, just an evening, looking at different stars, you'll see they're really quite different. Every single one is quite different from every other one. It's very, very interesting. But the surface temperature is a good place to start. So we can assign some sort of apparent temperature. Now, is this the real temperature of the surface of these things? What's the difference between the real temperature and the apparent temperature? This is a big boy question. Yes, take a stab at it.
I want to say apparent temperature is what would mathematically make sense, and then the actual temperature is the legitimate temperature or the actual vibrations of the atoms.
I think you're on the right track. Anybody else? Maybe I should have said big girl question also for ladies. This is tricky, right? So all we can say from a material is what the rays are telling us, right? So the light from the surface of the sun, let's go back to the sun. We're going to always be going back to the sun. It's our laboratory. The rays tell us that it has a temperature according to this map that we've drawn. The problem is we made this map with a static body. It had no other motions in it, right? Now we know the surface of the sun is churning, it's roiling, right? So there's a lot of energy, a lot of motion, a lot of thermal motion that isn't going into the rays of the sun. So the surface of the sun is almost certainly way hotter than that temperature that we read out from the rays themselves, right? So we read that the surface of the sun, the black body temperature, the rays tell us that the rays are at about 5,800 Kelvin. But there's a lot of other heat going on. There's things crashing into each other everywhere that energy isn't going into the rays. It's going into those convective processes, right? So we don't really know the real temperature of these things. We just know what the light's temperature is. This is a little bit nuanced and crazy. Does that make sense to anybody? All right, so heat, this gets really, we get into like high level thermodynamics really quickly. The point is that there's partitions, there's different modes that heat can exist in. It can be motion that goes into the actual light. It can be motion that goes into the actual translation of the atoms around the surface. It can actually go into the electricity that's going on, all that magnetism and electricity that we saw at the surface of the sun. That's taking up some of the heat too, right? So the real temperature, if you were to stick a thermometer in the thing, it's going to be very different than what you see just from the light. That is just the light temperature. Yeah.
So is the surface of the sun closer to its apparent temperature or the estimated temperature of its core in the gaseous model being like a bajillion?
Oh, I don't think it's that much. I doubt it's that much. I don't know. I wouldn't put a number on it just off the top of my head, but I would say it's probably a few thousand more than it looks like it is. And some parts of it might be really hot, like when you see those X-ray flares coming off. So sometimes these big sort of avalanches, let's say, for lack of a better word, like these big collisions happen on the surface of the sun. Maybe a flare, a big piece of like the surface licks off and then crashes back down and sets off an X-ray flare, right? That's a huge amount of thermal motion that's happening in that collision. That's like the equivalent of just like two aircraft carriers running into each other at like 1,000 miles an hour. I mean, it's a tremendous amount of heat generated. So parts of the sun surface are probably much hotter than others, depending on what's happening. But there must be some temperature which isn't accounted for by the rays, is my point. Yeah.
Or the temperature reduced by mantis shrimp's punch.
Yeah, exactly. Very hot right at the tip there.
Fun fact, its punch is able to create a cavitation bubble that is as hot as the apparent temperature of the sun.
So this is all right. So this is good. It's good that we can assign apparent temperatures. It helps us understand some general trends, but we do have to be careful. And so each one of these, what I'm going to try to paint for you is that the nuances of the work left to be done in terms of classifying these stars, it really involves understanding a lot more about what's actually happening at the surface and in these bodies, because to actually make those assignments, we probably need more information. But we can start off with that. So we have temperatures. Let's do one more little piece. So I already mentioned this part, which is really nice. We can actually look at the atmosphere. This is what I was talking about with Chabelsky's star. So we can see what's going through by which lines are excluded from that continuous spectrum. So we got the temperature. We got information about what's going on in their atmosphere. That's pretty cool. And so this leaves us with the ability to actually start to say something about putting these things on a continuum together. Let's start there next time. Let's start with the actual spectral classes next time. Really cool story. I want to make sure I get it all out. It was developed by a bunch of ladies. And yeah, we'll move on from that. We need to figure out how it is you see how far these things are, how bright they are. It's going to get really interesting here in a second, I promise you. All right, guys, have a good week. We'll see you on Thursday.